Okay. So today we're going to do a couple of things. One of them is just to talk a little bit about the relationship between plain language and the way we talk about things in plain language and what they really mean mathematically when it comes to probability and in particular independence. And then we'll look at some applications of this notion of independence. So how it can help you. So we've seen what the definitions are and seen how you can prove that certain things are independent. But what's the more common use of independence is when someone tells you that something is independent, or you design an experiment so that a bunch of events that might take place in that experiment are independent, then it lets you compute probabilities more easily. So first about the language. So we've often talked about events. We might have events A and B, and already you'll see that I often write this, and I say A and B. So meaning that A and B both happened. You might see that in some other places to look like this. This is the logical AND operator, and you've seen, so this is AND, and this, when I write things like this, I use the word OR for this thing, but it's really A union B, and that corresponds to the logical OR operator. And even before you studied probability, when you studied sets, you see that actually these things are related. In fact, the definition of the intersection of two sets A and B actually uses this operator, right? It looks for the elements X that are in A and are in B. That's what's in this thing. And the same thing here. The union of A and B takes the elements X that are in A or that are in B. And so this is a natural way to talk about it. We've been doing it all along. And so, we often define the things we talk about, we define in terms of, two things happening this way, in terms of these logical propositions. So let's look at an example. So let's say you have a probability space which is our coin tossing probability space, heads, tails, and for everything in this space, each one is equally likely, so each one has probability of half, and that's for each outcome in that space. And you might have another probability space that's coin toss, one for rolling a die, with 6 possible outcomes. And in this case, each one is equally likely, so each one occurs with probability 1/6. That's the probability function on this space. And someone might say, let's consider what happens when we toss a coin and roll a die. And so the wording for that might say something like, toss a coin and roll a die. And they might throw in this word independently, whatever that means. Okay. And let's give a name. The coin can be called C. The die can be called D. So when someone says something like this, that essentially they're defining a new probability space, a compound one. The set of elements that are in that space are given by what's called the Cartesian product, SC cross SD, which is what you think it is. It's a set of things that come in pairs. The first thing is a coin tossing outcome, and the second thing is a die rolling outcome. So that looks like H1, H2, H3, H4, H5, H6, T1, T2, T3, T4, T5, and T6. Okay. What is the probability function associated with this space? Well, the only sort of clue, and this is the way this is always used, the way you use this, is they write this word independently here, which is taken to mean that, well, the following. So the probability of any particular event, let's say the coin and the die, and let's write it this way, coin equals little c, and the die equals little d. So the probability that the coin comes up with one of these outcomes and the die comes up with this other outcome is just the probability that the coin comes up one way times the probability that the die comes up the other way. And so that's where this, when you, in this plain language, when they say you do these two experiments independently, that just means that in the probability space that's the product of these two things, then you can get the probability of any particular outcome, because it's just a pair of things like this, you just get the probability of the first one times the probability of the second one. And in our case, that's always going to be, in this particular example, 1/2 times 1/6 is 1/12. And each of these 12 outcomes is equally likely. That's all that means. All right. So it's going to happen a lot, and the more you work with these things, the more often this kind of plain language gets used. So we'll look at a couple more examples. Well, before we do that, let's do this rather silly lemma. Let's take A1 to be n, be a sequence of mutually independent events. Then the probability of A1 and A2 and equals something. Also, the probability of A1 or A2 or AN equals something else. So what goes on the right-hand sides here? A1 through AN are a sequence of mutually independent events. What's the probability of A1 and A2 and A3 and so on up to AN? Yeah. Yeah. So it's just going to be the probability of A1 times the probability of A2 times and so on probability of AN. Why is that? Well, the definition of mutual independence says that if I take any subset of these N events and ask you what the probability that all the events in that subset happen is, it's just the product of their individual probabilities. So this is just a very special case where the subset that of mutual independence, where the subset that I'm interested in is the subset that is all of the events. So the full set. What about this one? Anybody know what goes there? Yep. No. Yep.
Repeat that and subtract all the overlapping ones. But no.
So I'll write it down and then we'll see if we can figure out what it means. So it's 1 minus something. And the thing that it's 1 minus is a whole bunch of other 1 minus somethings. 1. Okay. So let's think about this logically for a second. A1 or A2 or A3 or A4 and so on. So it looks like we're using the complement rule here. And what's over here is all of these things. So A1 or A2 or A3 and so on up to AN, when is that true? Well, that's true when A1 happens or A2 happens or A3 happens and so on. When is it false? It's false if A1 doesn't happen and A2 doesn't happen and A3 doesn't happen and so on all the way up to AN. So this somehow seems to be the probability that none of these things happen, and the probability that at least one of them happens should be 1 minus that, right? And if you don't like that line of reasoning, it comes from De Morgan's law and a lemma that we saw last class. A1 So let me negate and negate. Okay. So I take the complement. Remember, this is just a set. This is just the union of sets, so itself is just a set. So I can take the complement of that thing, which is everything that's not in the set, and then I take the complement again, which is everything that is in the set. So this is a trivial sort of thing. Yeah, take the complement twice, you get the same thing back. So anyone remember what De Morgan's law does? Yeah. Yeah. Turns the ors into and, so and does what to them in addition to that? So what De Morgan's law does is it takes this big bar that's over all of the ors here and pushes it down so that it's over each individual A. So that's just the first bar. There's still the other one on top of it all. And the things that used to be ors become ands. And that's what we just talked about, and so this should be negated also. That's just what we talked about, this doesn't, so the negation of this happens or this happens or this happens or this happens or this happens is none of them happen, which is this doesn't happen and this doesn't happen and this doesn't happen and this doesn't happen and so on. So that's just De Morgan's, the way you remember De Morgan. Well, and now we're golden. What is this thing? We have a negation out here, so that's just 1 minus the probability of A1 naught and A2 naught and A3 naught all the way up to AN naught. Right? I have this negated event out here, so that's the probability of the probability of not this is 1 minus the probability of this. And, well, we saw a lemma last class that said if events are independent, then their complements are independent. So A1 through AN are independent, therefore not A1 through not AN are independent. So we apply the definition. So this is the probability of not A1 times the probability of not A2, and so on, times the probability of not AN. And what's the probability of not A1? Yep. Just 1 minus the probability of A1. So then this whole thing becomes, this is 1 minus the probability of A1. This is 1 minus the probability of A2. And so on, all the way up to 1 minus the probability of AN. And that's what we're trying to show here with 2. This is equal to this, is what this says. And it's easy to get confused when you're working with these symbols, but it's a little, it's not too hard to remember as long as you think about it slowly and carefully, and just in the way that I just described. And the main thing to sort of remember is this thing that A1 or A2 or A3 or up to AN, the way I like to think about it is that is true if you were thinking of it in terms of logic. It's true if at least one of these are true. And it's false only when all of them are false. And so that's where this is, basically this is coming from. This is over here, this is the probability that all of them are false, and therefore the probability that at least one of them is true is 1 minus that. So another classic example is you flip a sequence C1 to Cn of n independent coins. And what does that mean? There's that use of that weird word independent, not in the way that we're used to seeing it in terms of random variables. Well, that means that the space that you're working in is this, the set of outcomes is heads, tails, times heads, tails, times heads, tails, times heads, tails, n times. So in that way you get that the elements of that space are sequences of length n. And the probability of any particular sequence is just going to be the product of each of the things in that sequence. So each one is going to have probability 1 over 2 to the n. So this is, looks like this. So that's S is C1 up to Cn, such that each of these things, C1 up to Cn, comes from the set heads, comma, tails. And the probability of any particular thing, so let's make these capital C's. The probability of any particular outcome, little c1, little c2, up to little cn, is just going to be 1 divided by 2 to the n. The size of this space is 2 to the n because there's 2 choices for this one, 2 choices for the second one, 2 choices for the third one, all the way up to the nth one, and this is the probability of any particular thing. Now, here's a question. What is the probability? So, you know, as word problems, these will be stated like I toss a coin n times. So that really means there's this sequence of n independent flips. What is the probability that all coin tosses are heads? So toss a coin n times, what's the probability that all the coin tosses come up heads? One over 2 to the n, because that really, in this space that I just described, that's the probability of one particular event, I mean, one particular outcome. It's that one. This is just a set of, this is an event, which is a set, which has only one thing in it, where it's all heads. And we just said that everything in this space has probability exactly 1 over 2 to the n. Or if you don't like to think about it that way, this is the probability that C1 equals heads, and C2 equals heads, and C3 equals heads, all the way up to Cn equals heads. And this probability is a half, this probability is a half, this probability is a half n times, and this up here we said all of those were independent, so the probability that each of them happens will be, probability that they all happen simultaneously is a half times a half times a half times a half n times, which is again 1 over 2 to the n. All right, then how about the following? What is the probability that we get at least one head? Toss the coin n times. What's the probability that the coin comes up heads at least once? Yep. Yep. So that's this question that's saying, what's the probability that C1 equals heads, or C2 equals heads, or C3 equals heads, and so on, all the way up to Cn equals heads. We have this part 2 of this formula that tells us that that is 1 minus something, and it's 1 minus the first, it's a product of things, and the first one is 1 minus the probability that C1 equals heads. And the next thing in the product is a 1 minus the probability that C2. And then the next thing, and so on. And this is where the coin tossing thing can be misleading, because probability of equaling heads and tails, or tails is a half, so 1 minus those probabilities is also a half. So you have to be careful when you apply these things to remember that it's really the 1 minuses that you're getting here. If you forget with coin tosses, it doesn't matter. You'll get the correct answer even though you forgot a step. But this is 1/2 times 1/2 times 1/2 n times, so this is 1 minus 1/2 to the n. All right, and just so you get a feel for this, this probability that all the coins come up heads, when n gets big, what does that probability look like? Is it big or small? Small. It's heading towards 0, right? 1/2 to the n is heading towards 0. So the probability that all the coin tosses come up heads is getting really small. Here, the probability that one of the coin tosses, at least one of the coin tosses comes up heads, when n gets big, what's that heading to? 1. So as n gets big, it becomes overwhelmingly likely that you'll see at least one head. Exactly what we expect. So let's see how we can use these things in some real applications. And today we're going to see some sort of easy thing, but already there's a clear application to computer science or computer engineering, if you like. And then we'll see one that's just a beautiful classic algorithm that's actually really relevant today in the era of big data. So you guys may or may not know this, but so how many of you here have bought a computer before? Or own a computer, anyway? Yeah. That computer, do you know if it has more than one core, typically? Yeah. So you may know then that companies sell things like 8-core processors, 4-core processors. Sometimes you'll see weird numbers, 6-core processors, 2-core, and maybe even like at the bottom of the parts barrel, you can find 1-core processors. What you may not know is that all of those processors were made the same way. So the level of precision at which they manufacture these things right now is, right on the bleeding edge. So much so that on that tiny little chip, they can pack in 8 cores, sometimes even more. And they do this, using super precise manufacturing processes, but they're always right on the edge. They're so precise that there's a chance, that some wire which is supposed to be in there, which is really just like a few atoms of something wide, that wire doesn't work. Just even despite their best efforts, that happens. Something gets contaminated, or something just doesn't get dropped in the right place, and it just doesn't work. So they manufacture these things, and maybe they manufacture something with 8 cores. It comes out of this manufacturing process, And then they hook it up to a tester, which tests these cores, because some of them don't work. And the tester says, okay, I tested them, and actually this core number 2 doesn't work, and this core number 7 doesn't work. Now, the natural thing you would think is you try to make an 8-core processor, 2 of them don't work, you throw it in the garbage. No, you don't. You sell it as a 4-core processor, or 6-core if you're doing those weird things. So if you own a 4-core processor, it probably actually has 8 cores on it. Some of them may or may not work, or some of them may have just been turned off because they wanted to do that, to offer something like that. Okay, so this is a notion that's used in processor manufacturing these days, and forever basically, and it's the notion of a parallel. It's called a parallel circuit. And at the extreme case, when do they really have to toss one of these things in the garbage? They only have to toss it in the garbage and not be able to sell it to anyone or even give it away to charity if all 8 of these things fail. If there's even one that survives, you can still sell it to someone and treat it as a low power processor or something. You can go in your netbook or whatever your cheap thing is, or you give it away to a charity. So the only time that it really needs to be thrown in the garbage is when actually the tester runs and says none of these are working. So the general picture of that is what's we call a parallel circuit. You have a bunch of inputs. They all get split off. Into these circuit C1, C2, C3, all the way up to some number Cn. And you say that, so this is a parallel circuit. And you say that the circuit works if C1 works, or C2 works, or C3 works, or Cn works. And at the other extreme, which you don't see too many examples of in microprocessor manufacturing, precisely because it's at the other extreme, is what's called a sequential circuit. And this you can think of, in terms of circuits, or you can think of it in terms of like just working on things in the workplace, right? So let's say that you and your friends want to do the assignment for this course. There's 10 questions. You and 10 friends get together, or you and 9 friends get together. So there's 10 of you in total, and you want to get 100% on the assignment. So you say to friend 1, okay, you do question 1, you do question 2, friend 2 does question 2, friend 3 does question 3, and so on. So everybody's assigned one question. You're only going to be happy if you get 100% on the assignment. So when is this going to work? Well, it's going to work if the first person does their job. So first person is circuit 1, and the second person does their job, and the third person does their job, and the nth person does their job. If any one of them doesn't do their job, you're not going to get 100% on the assignment. And we'll see in a second, it's a bad idea to design circuits this way, because this thing is sequential circuit. Works when C1 works and C2 works, and so on, Cn works. So this is the two different kinds of circuits. We'll pretend that the circuits are, we'll just analyze both of them. Let's say that C1 through Cn each work with probability P. And again, I'll use that word independently. And again, that somehow means that there's this underlying space. You know, if I ask you about the event, does C1 work and C3 work? That's just the probability that C1 works times the probability that C3 works. So that's what we're going to assume. Then, given that, what is the probability that the sequential circuit works? That's the easy question. So we have a sequential circuit. It's the one far on the left. It's made up of these things. Each one of them fails. Each one of them works independently with probability P. What's the probability that the whole circuit works?
P to the power n.
Yeah. So that's just the probability C1 works and C2 works. And so on. Cn works, which is just equal to the product of those probabilities because they're supposed to be independent. This is P, the next one is P, the next one is P, the next one is P, and so on. So this is P to the power n. And we already decided that as n gets big, unless P is equal to 1, this thing is heading towards 0. So the longer and longer you make this circuit, the less and less likely it is to work. All right, and next question, what's the probability that the parallel circuit works? Well, we just write down what it means for it to work. So that's just the probability. So the parallel circuit works. That's if C1 works, or Cn works. What's that equal to? Yep.
1 minus P times 1 minus.
Yeah. So this is just going to be the probability that one of them works is, at least one of them works is 1 minus the probability that none of them work. C1, I'll write not works. And all the way up to Cn not works. Excuse my grammar. And that is equal to 1. Probability that C1 works is P, therefore the probability that C1 not works is 1 minus P. And the same is true for C2, C3, and C4, all the way up to Cn. So we get 1 minus P to the n. And that thing we saw is heading towards 1 as n gets big. And so you see why this is the way people like to manufacture things, is because the probability that you get something that works at least a little bit in this multi-core thing is tending to 1 the more of these things you add. Yeah? Because the probability that C1 doesn't work is 1 minus P. The probability that C2 doesn't work is 1 minus P, and so on, all the way up to the probability that Cn doesn't work. And these things are supposed to be independent, so they're, you just take the product of those individual probabilities. So there's one step between here and here where you take product of C1 not works times product of C2 not works times product of C3 not works. And so on. Well, because you have to work through it slowly and say, what does it mean to say that C1 works or C2 works or Cn works? Well, it means at least one of them works. What's the opposite of that? The opposite of that is none of them work. So if I can compute the probability of the opposite thing, the complementary thing, that's this, none of them work, then the probability of the original thing is 1 minus that. That's the complement rule.
Oh, yes, it must be. If it doesn't work, I'm subtracting by 1 to get the probability of 1.
Yeah. So you have to go through these things carefully and slowly. For example, a common mistake here is to end up with a 1 minus P to the n here, which is only correct when P is a half. That's why coin tossing is not the best example of these things. But you see what we just did here is exactly what we did for coin tossing, and these are the two instances of that lemma about the probability of A1 and A2 and A3 up to AN, and the probability of A1 or A2 or A3 up to AN. So this is really an example of like you design an experiment. In this case, you manufacture your processor to have these n independent cores on it. So you design it so that the probability that it succeeds is high. And the things you need to make sure, if you want this to be reasonable, is that those core failures are actually independent events, not the greatest assumption for processor manufacturing, because if someone leaves one hair in the manufacturing room, then that can lie across the whole chip. That's one hair is long enough to cover the chip several times, and then nothing will work. So they're not necessarily independent, but if it's a really clean room and the only issue is, some amount of processor ink in the stamp, some blot didn't happen in one place, then it's kind of not a bad thing. Not a super unreasonable assumption. Okay, good. Now for a very cool application. So the application is random sampling in a data stream. So what's a data stream? Well, it's a stream of data. That's one way to say it. But it's better to think of it in terms of examples. You know, all these online retailers and search engines and things, you know that they're watching what you're doing, right? So Amazon, for example, when you're shopping on Amazon, and even when you're not shopping on Amazon, but especially when you're on the Amazon website, they have extremely detailed information about what you're doing, including like even things as maybe detailed as where your mouse is on the screen on the web page that you're looking at. So tons and tons of data. And you're not the only Amazon customer in the world. There's billions, maybe, close to, on that order of magnitude. So Amazon is monitoring what all of these people are doing all of the time that they're on Amazon. That's a huge amount of data that's coming in constantly. Now, so much, in fact, that even though they have incredible resources, they can't store every single piece of data that's coming in. So a lot of it they do store, and they remember it forever, but just the magnitude of it all is too much to store all of it forever. Okay. So the way that they get sort of global information about people's behavior on these sort of really fine things is they do random sampling. So how do they do that? Well, the most basic thing they might want to do is, over the whole course of a day, they might want to sample one of these events. So all of these events happen over the course of a day. They want to sample one of them. So let's call these things, you know, you have this data stream D1, D2, D3, D4, all the way up to DN, and I'll put a big N there because it's really a big N, not a little n. A lot of data, more than you ever want to store, and you want to pick one at random. Now, the easy solution to this is to say, well, first you wait for it all to come in. So this is option one. Wait until the end of the day. Now you know how much data has come in, and pieces of data, and then pick a random integer in 1 up to n, and return dn. The random integer, let's call it r, and return dr. I mean, that's going to give you, if you pick a uniformly random integer in 1 through n, then you'll get a uniformly random data item here. Each item will be returned with probability 1 over big N. Problem with that is it requires that you wait till the end of the day and store all of the data. So you might say, don't wait till the end of the day, let's just change the order of these things. Pick a random r in 1 to n. Wait for dr and return it. What's the problem with that solution? Yep. At the beginning of the day, we don't know the value of n because n is the number of events that's going to happen today. So at the beginning of the day, those are the events that are going to happen today, but we don't know in advance exactly how many people are going to be there, how many people are going to use our site, how many events they're going to generate. So I actually can't do this step because I don't know the value of n. So this one doesn't work. On the other hand, this one was nice because if we could do this, we'd be really happy because we don't need to store anything except for one piece of data, right? We just let the data go by, go by, go by, counting it as it goes along. We need to store the integer r that we picked, and maybe an integer I, which keeps track of how many data items we've seen. And the moment I is equal to r, we return the item we're currently looking at. So we would like a solution that captures both of the benefits here, that it only ever has to look at one data item at a time, and at the end of the day, it still returns a uniformly random data item. So here's what you do. So let's take n, start with n is equal to 1, and you say, while it is not the end of the day, meaning there's still going to be one more event, let's say d, maybe better not to call it n, let's call it I. di is I is the next event. Now you want to decide if you're going to save di or not. So you're going to have to make some decision. But once that decision is made, if something, then we're going to take our sample S and say that thing is equal to di. Else we will discard di. And then finally, at the end of the day, we're going to return S, our sample. So we need to decide how are we going to decide? There's only one piece of code missing here, which is what do we put in this if statement? Any ideas? Yep. What's that? No. I mean, it's some random thing, but basically, you want to put some probability here that's going to make all of this work out. And you want it to be such that the probability that you return any particular item should be 1 over n, where n is the number of items you've seen all day. This means assign, make S equal to di. Save it, because this is the sample. For now, this is what you think is going to be the sample. Maybe later, you'll decide something else should be the sample, but for now, it's going to be this one.
D represents data.
D is the ith item of data. Oh, and I should say, let's do it this way. Start with I equals 0, then say I is equal to I plus 1. So the first thing we see is going to be D1. And then at the end, the last thing, at the end of this, the value of I is equal to n. So with some probability here, we want to keep the current item. What do you think that probability should be? So these things are coming along, and we'll see actually that there's really only one possible choice, and we just have to hope that it works. So the day is going along. We've maybe been sampling, keeping one of these things, and now we don't know it at this instant, but this is the last data item in the set. After this, the day's over. We don't know it right now, so we can, at this point, we can choose to discard this thing, and which means after this, we're going to return our previous sample, or we keep this thing, in which case it's going to be the thing that we return. What's the probability that we should keep this thing? There's only one answer that can work. Not 0.5. That would mean that the last thing has probability at half of being returned, even though there's billions of things. That would be way too much. We want all of these to be returned with equal probability. But this last one, it gets returned with exactly the probability that we choose it, because nothing else is coming later. So that means we better choose this thing with probability exactly 1 over n. Because it's the only thing that can work if we want everything to be equally likely. Equally likely means we want each of these to be our random sample with probability 1 over n. And so in particular, this last one, we should choose to have it with probability 1 over n. And we can do that for the last one because we know the value of n at this point. What is the value of n at this point? It's the value I. I is counting how many items that we've seen. So instead of saying if here, let's say with probability 1 over I. We do that. And else, which means with probability 1 minus 1 over I, we don't bother. So let's see if this makes any sense at all. First item of data comes along. I is equal to 1. So with probability 1 over 1, we save this one. That makes sense, right? Because that could be it. There might only be one event all day. If we're going to return a sample event, it has to be that one. Okay. So this guy, with probability 1, we save it. And then the second item comes along with probability 1/2. We save it. And with probability 1/2, we don't save it. So if that were the end of the day, and now we return whatever we have. So does that work? Yes, because at the end of that day, if this is where the day ends, with probability 1/2, we'll return D2 because we decided to save it. And with probability 1/2, we didn't save D2, which means we're still holding on to D1. So we would return that. And we could try and do up to here, but already that's going to get a little complicated, so maybe we should just do the general case. So a claim I don't know, let's call this thing sample stream. Is that for any r in 1 to n, the probability that sample stream returns dr is exactly 1 over n. That seems insane, but that's what we're going to try and prove. We know that it's true for one value of r. We know that it's true for r equals n because, yes, indeed, we pick this one with probability 1 over n, and if that happens, we return it. But why that should be true for all these other ones as well? I mean, those other ones we picked not with probability 1 over n, but with this 1 over I, where I was the number of things we've seen so far. All right, so let's try and prove this. And let's say for each I in 1 to n, let Ci be the event we save di, and let's even give everything 1, 2, 3, 4, 5, 6 in line 6. That means we decide to hold on to di at least for a little while, save it in S. Okay, so now let's look. We're interested in the probability that sample stream returns dr. So when does that happen? The thing is running for a while. Here's dr. And I'm interested in what the algorithm, the executions of the algorithm, where the thing that it returns is this item, this particular item dr. So what happened before that, doesn't really matter, right? It's what's going to happen next that counts. So what has to happen? Yes, and? So a bunch of things have to happen from this point on. We better pick dr, but we better not pick dr plus 1, otherwise dr is gone. We better not pick dr plus 2, we better not pick dr plus 3, and so on, all the way up to we better not pick dn. If all of those things happen, then dr is going to be the thing that's returned. So that means that this probability that we return dr, we have a name for it. We have a name for each of those individual events. We have to save dr. So that means the event CR has to happen. And CR plus 1 better not happen. And CR plus 2 better not happen. And so on, all the way up to CR or CN. And now, are these events independent? Well, each one of them basically is controlled by some choice that we make here. So if this algorithm really has a random number generator that can pick independent random numbers available, then yes, the probability that I choose di, or the event that I choose di should be independent of the event that I choose di plus 1. So the underlying assumption, and it's the thing that we use all the time when we make randomized algorithms, is we can choose uniformly independent random numbers, or in this case, we can run a random test, toss a coin that comes up probability 1, or comes up heads with probability 1 over I. And all of those coin tosses are independent. So, like I said, mutual independence is super hard to prove. Usually you assume it or you design your experiment so that it's the truth. And in this case, it means you use a random number generator for this algorithm that really has that property. So if that's the case, then we're just interested in, this is the probability of CR times the probability of not CR plus 1 times the probability of not CR plus 2, all the way up to the probability of not CN. All right. Good. So far, so good. Now we just need to know these individual probabilities and do our calculation and hope that it all works out. What is the probability of CR? Or maybe we should just ask the generic question. What's the probability of CI? Well, this is, we save DI in line 6, and actually the definition is it happens with probability 1 over I. So keep that in mind. Probability of CI is equal to 1 over I. And that means the probability of not CI is 1 minus 1 over I. Now we have everything we need. Let's do it. So this is probability of CR is 1 over R. Probability of not CR plus 1 is 1 minus 1 over R plus 1. Probability of a not CR plus 2 is 1 minus 1 over R plus 2. Do even one more. All the way up to, and let me see. This is 1 minus 1 over n minus 1, and this is 1 minus 1 over n. Okay, good. Does anybody see what to do next? This is where a little bit of familiarity with algebra helps out. So often when you see something like this, it helps to write these in some nicer way. What is the nicer way? So we got 1 over R, that's pretty nice already. But maybe this thing we could write differently. So we should have an R plus 1 on the bottom. And what's on top? Well, this on top should be an R plus 1, that's this thing, but then we subtract 1. Right? So that's what the top should look like. Yeah? Okay, let's do the same thing here. We want an R plus 2 on the bottom. So on top, we better have an R plus 2, but then we subtract 1. So we get that thing there. And then the same thing here. We put an R plus 3 on the bottom. On the top, we should have an R plus 3, but don't forget to subtract the 1. And we keep going. And here we're going to have a n minus 1. And we'll have an n minus 1 minus 1. And finally, n and a n minus 1. Is this as simple as it could be? No, these things on the top look stupid now, right? I mean, plus 1 minus 1 plus 2 minus 1, we should simplify those. Yep.
1 over R plus 1 over
Here? Well, these are just the probabilities, right? That's this formula here. Probability of CR is 1 over R. Probability of not CR plus 1 is 1 minus 1 over R plus 1. So, okay. So let's clean these things up. Instead of this being r plus 1 minus 1. This is just r. Instead of being r plus 2 minus 1, I think this is just r plus 1. R plus 3 minus 1, maybe that should just be r plus 2. Instead of n minus 1 minus 1, this should be n minus 2. And this guy's okay. Now what? Anybody see it? Yeah. This is a product of a whole bunch of fractions. And look at this. We have an r down here, and we have an r up here. Those are going to cancel out. We have an r plus 1 down here, and we have an r plus 1 up here. Those are going to cancel out. R plus 2 down here, r plus 2 up here is going to cancel out. R plus 3 will cancel out with the next one, all the way up to, there'll be something down here that cancels out the n minus 2. The n minus 1 down here is going to cancel the n minus 1 up here. What's left? We've got a 1 on top and an n on the bottom. Magic. So, without knowing how much data we were going to see at the beginning of the day, so we didn't know the value of n, and without having to store all of the data, we've made an algorithm that for any particular r is going to return dr with probability exactly 1 over n, which means that that algorithm is returning a uniformly random sample from the data without knowing the size of the data in advance, without storing the data. So all of the nice things that we wanted. And the only way we could figure that out, I mean, the only way to devise that algorithm and even prove that it's correct is using the tools that we've learned in this course, right? There's no way around that. This is not a trivial calculation, not a trivial result at all. This is a celebrated algorithm, though I forget the name of the person it's named after. It's not Floyd, Simon maybe, I don't know. It doesn't matter because whoever it's named after was certainly not the person who invented it. But really this is, finally, you may be saying, hooray, finally we used something in this course to prove something that's definitely relevant to computer science. I mean, this is analysis of an algorithm showing that it does exactly what you want, and a really non-trivial and clearly thought out application of probability. So that's a good place to leave it for today. If you have any questions, you can come and ask.